Our team addressed the problem of developing a spirit blending model. This problem was brought to us by Mike Blom of Blom Brothers Distilling Company in Galena, Illinois, and he wanted us to generate a calculator that would dictate the process of blending two spirits together. A bit of a background on the spirit making process. It all begins with grains such as corn, rye, wheat, or barley, and then these grains are put through a process that extracts the alcohol out. And the steps are mashing, fermentation, distillation, maturation. It is after this entire process that our calculator is examining. And some people like to blend two spirits together in order to either enhance their texture or flavor or change the proof of the overall alcohol. And this is the process that Mike Blom would like us to create a calculator for.
So when building this calculator, we had to explore a lot of aspects and concepts when building it because there's a lot of things that cause the alcohol to behave in a certain way. So one of the things we need to observe was the aspect of temperature correction. And this is an important aspect to look at because alcohol is usually at a standard around 60 degrees Fahrenheit or 15 degrees Celsius, and most alcohols, when they're mixed, won't have that standard because some will be warmer or some will be colder. So because of that, we need to take a factor for correction for that. The second thing with volume is also the aspect of volume reduction, because what happens with alcohol is that when you mix them together, there's a slight change in the volume being reduced, and it's mostly because of the fact of how the chemical composition is built. And it's from a concept called intermolecular forces. So basically, since alcohols consist of ethanol and water, the way the ethanol interacts with the water will cause it to compress or attract and shrink. And one of the main ones that causes hydrogen bonding, which is the main intermolecular force for causing it. So to resolve that kind of problem, we also explore another chemical concept called partial molar volumes. And partial molar volumes is basically the contribution 1 mole of ethanol or water contributes to the mixture of the solution. So this is also important to look at when we're given the proofs mentioned earlier because we can take the concentration of it and also with the partial molar volumes we can figure out how much it contributes to how much volume we end up losing. And lastly, another thing we need to explore is the volume fluctuation from weight and volume because what ends up happening is that volume is not always a consistent measure because temperature will always change later after the process. So we have to measure also in weight because weight doesn't change because the moles don't change as well with it when we measure the molar mass and also changing from moles.
So after examining the different important factors that we'd have to take into consideration that extremely complicate this process, we were able to identify a few simplifying assumptions. The first one is that we decided that the spirit would consist solely of water and ethanol. There would be no other chemical additives, such as flavorings, that would change the characteristics of our final blend. The second one is the idea of partial molar volumes, which was used in the volume reduction. And our simplifying assumption is that these remain constant, where in real life these would have a slight temperature fluctuation. And the last assumption that we made is that the proof corrections for temperature were given to us by the government data from the Alcohol and Tobacco Tax and Trade Bureau.
So now in order to calculate our spirit blending model, we wanted to have inputs of the proof of both spirits, the temperature of both spirits, as well as the weight of the first spirit that we're adding. And in order for our model to work, it should output the volume of both spirits, the true proof of both spirits, which is the proof of the spirit at 60 degrees Fahrenheit, and the weight of spirit B, as well as the final volume and the final mass. So the first step of this is to correct for temperature. We wanted to correct for temperature first so we didn't have to worry about it later throughout our process. The government gives us a standard temperature at 60 degrees Fahrenheit for proof, and we'll also use that degree Fahrenheit for our volume as well. In order to correct for this temperature, we added an apparent proof input and a temperature input into our model. The apparent proof is what the hydrometer measures, and the temperature is the temperature of the spirit at when we measure that from the hydrometer. The government provides a data table in order to correct for this. So say we had a spirit at 70 proof, but it was 65 degrees, we could go to the intersection of the government given table in order to correct for that. So now the first thing, now we have the true proof of our spirits, we want to convert this weight of spirit A into a volume. To do that, we found the density of our solutions, and we found that density, as given to us by the general density equation of a solution, is a linear relationship between water and ethanol in this case. The density of ethanol is 0.789 grams per milliliter, and the density of water is 1 gram per milliliter. So using the general density equation of the solution, we were able to derive that our density equation was equal to negative 0.0011 grams per milliliter times the proof of the spirit plus 1. And then now that we have the density of our spirit through the mass, we can calculate for volume by getting volume is equal to mass divided by density. Now that we have our volume of spirit A, we can actually calculate for our volume of spirit B because we know our desired end proof and we know the volume of spirit A. The proof desired equation is how we get to our end proof. So what we decided for that was that the proof times the volume of spirit plus the proof times the volume of the second spirit over the total volume gives us our proof desired. One assumption that we made that interacts right here is that the volume of A plus B in this case is 1-to-1 volumetrically. So that means that if we add volume A and volume B together, it wouldn't reduce. We thought that was negligible though in this case because we would still have our correct parts alcohol to parts water. And then solving this proof-derived equation, or proof-desired equation for the volume of B gives us, the volume of B is equal to proof times volume of the first spirit minus the proof desired times the volume of the first spirit over proof desired minus the proof of the second spirit. So now that we have the volume of both spirits, we can convert this volume into moles. So in order to do this, we first have to find the amount of mass of each molecule within the spirit. So to do this, we first take our proof and we get it into a percent alcohol. So to do that, we take the proof divided by 200, because as we know that proof divided by 2 is the alcohol, and then to take that over, we take that over 100 to get a percentage. Now to get it in a mass, we take that times the volume, which we already know from earlier in our calculator, times the density of ethanol, which again is 0.789 grams per milliliter. And then we take our mass of a molecule within a spirit over the molar mass. So to get this, we break this down into number of moles for ethanol and number of moles for water. Now that we have the number of moles of ethanol and number of moles for water for both spirits, we can add those together to get the number of moles of water and number of moles of ethanol for our final spirit. And then this is where volume reduction comes into play. Using partial molar volumes, as we explained earlier, and knowing that we assume that our partial molar volumes are constant, and the partial molar volume of ethanol is 58 milliliters per mole, and the partial molar volume of water is 18 milliliters per mole. This means that for every mole of ethanol that we add to it, we're going to add 58 milliliters of volume to our solution. So now that we have our partial molar volumes and we have the number of moles of each molecule in it, we found that the volume reduced equation is equal to the number of moles of ethanol times the partial molar volume of ethanol plus the number of moles of water times the partial molar volume of water. So this gives us our final volume, and mass is easy to calculate, seeing as we can just add the mass of spirit A and the mass of spirit B, and that'll give us our final mass. So that gives us our outputs, our goal outputs of our calculator.
Once again, our problem was to find a spirit blending calculator which would model mixing one spirit with one proof with another spirit with another proof and finding a desired alcohol input and output. As you can see here, here is the Excel spreadsheet that we came up with, where the green cells are your inputs and the blue cells are your outputs, where we have the apparent proof for each spirit, the true proof for each spirit, the temperature, and also the mass and volume that is produced when mixing those solutions. During the calculation of our model, we made a few assumptions along the way. For instance, rounding occurs at some points during the model, especially when we factor in temperature from the government tables. This makes our model run a little bit more efficiently, but may slightly throw the numbers off. As well, gravity is considered consistent throughout the model, although that may change at some points during the mixing. We also assume that one-to-one mixing occurs for the benefit of the calculations, but we eventually correct that through calculations in our model, but this might cause some correction within our numbers. And finally, the partial molar volumes are considered consistent as well, despite the temperature and the molar ratio that may occur throughout the mixing. Here's an example of our model, and some limitations occur when you put inputs that have proofs that are less than 20, because the model recognizes this number as a number really close to 0, which would make the outputs 0 as well. Also, the real-world situations sometimes do not apply here. So, for instance, if you have an apparent proof of spirit A, say 190, and apparent proof of spirit B, say 20, like there, you cannot have a spirit outside of that range, so say a desired proof of spirit 10. If we were to have more time, we would expand on our model and solidify its accuracy and validity by experimentation with the actual mixing of alcohol. Also, we would factor in gravity and try to solve for proofs less than 20, so that way our model would be more correct. We would also have something for flavors to add to the whiskey to help the brewing companies with their process, and we would add a business economical effect to maybe provide cases, numbers, and money that they can make. We'd like to acknowledge our advisor, Dr. Mariah Bergen, and also Mike Blaum and the rest of the Blaum Brothers Distilling Company, along with Dave